Hi class, welcome to the last section of chapter 3. Today we're going to talk about polynomial and rational inequalities. Okay, so really what's going to happen is we're going to kind of throw it back a little bit to some previous sections. Chapters 1.8 we were dealing with inequalities and how to graph them. And in 2.3 we're dealing with graphs of things and looking at inequalities as well. So, so now that we have a better understanding of polynomials and rational functions, and functions in general, we can kind of combine these two sections. So again, we're going to compare polynomials to each other or to a rational or rationals to each other. So in 2.3, we're talking about when we have one function that's more than another function or less than another function, the intervals of existence for that satisfy that inequality, right? So that's kind of what we're doing. So the steps that we're going to take in this section are pretty much the same that we have for solving inequalities in general, right? Slightly different, but pretty much the same. So we want to zero out our inequality and simplify as much as possible. Factor everything we can after we zero it out, okay? We want to identify any zeros and any vertical asymptotes that we might have. And we want to determine if the function is positive or negative between the zeros and the vertical asymptotes. So in 1.8, we did pretty much the same thing. We zeroed everything out, factored, find the zeros or the vertical asymptotes, and found the sign. So that's really just what we're doing now. The only difference is that we're comparing two functions to each other rather than maybe like a polynomial. When is a polynomial greater than 1, right? Here we'll say when is one polynomial larger than another polynomial? Or when's one polynomial larger than this rational function? So things of that nature, right? So for our first example, let's solve when this fourth degree polynomial is less than or equal to this fourth degree polynomial, right? So the process is straightforward. We're going to zero everything out. So we're going to move everything to one side, right? So easiest is just to add this to that one because there's less things on the right side than the left. The other reason is, well, this is negative, so if we add it, we're adding things rather than having to have a negative 2x to the fourth on this side and, you know, things like that. So we'll keep everything positive. It's easier to deal with positive values. So when we move everything over, this is what we should get, right? A 2x to the fourth, right? When I minus this 3x squared, this 2, I'm sorry, I get negative 3. I get minus 1. The x, nothing happens. When I subtract 9, I get negative 1. So I really want to know when is this polynomial less than or equal to 0, right? Solving this thing is analogous to solving this inequality. The answers here is the same as this. It's really just me taking these two things instead of bringing them down to the x-axis. That's really what I did, right? I kind of subtracted one polynomial from the other to get a single polynomial that has the same characteristics as this inequality, right? So my possible zeros are going to come from here, right? So I want to factor this thing. It's kind of a large, so maybe factoring is not going to work. So I will find the possible zeros instead. The zeros of the constant and the zeros of the lead coefficient on the bottom, right? So my possibilities are plus or minus 1, okay, and plus or minus 1/2. So 4 possible zeros. Again, we always start with the easiest one. We'll start with x equals 1, and we'll do our synthetic division, right? 2, negative 3, negative 1, 3, negative 1. We always kick it off with a 0. 2 plus 0 is 2. Multiply is 2. Add that is negative 1. Multiply that is negative 1. Add that is negative 2. Multiply that is negative 2. Add that is 1. Multiply is 1. And we found our first 0. That's great. Okay, so that's one of my zeros. If you look here, you'll notice that the coefficients are 2, negative 1, negative 2, 1. So it's the same value, opposite signs. That's an indicator to us that we can actually solve by grouping. Okay, so we're going to take this resulting polynomial, factor out common terms out of both halves. Here the common term is x squared. Here I can just pull out a negative so that the binomial common factor matches with their signs, right? So I have a 2x minus 1 and a 2x minus 1. Factor that out and I'll have x squared minus 1 times 2x minus 1. And this is x plus 1 times x minus 1. Now remember, this is what I got after I found x equals 1 was a 0. So that means that x minus 1 is a 0, as well as these. So I actually have two x minus 1 factors. So again, don't forget when you have multiplicities, right? So now I have my zeros, okay? I need this polynomial less than or equal to 0, right? So the most obvious thing to do now would be to check the values for when these are less than or equal to 0, right? I already know when they're equal to 0, actually. But I want to check the points between the zeros, because if it's positive overall, then it doesn't satisfy this. If it's negative overall, then it does satisfy this, right? So again, I'm going to check values between these. So I want on one side of -1, so -2 works. I'll do some value in between -1 and 1/2, probably 0. Some value in between 1/2 and 1, probably 3/4. And then one value on the other side of 1, the easiest would probably be 2, right? So let's start with -2, because that's to the left of -1. So sign-wise, again, we're looking here. Negative and negative, but there's two of them, so that doesn't matter. So negative, a negative. Here will be another negative. Here I'll have a -4 and another negative, so it'll be 1, 2, 3, 4 negatives. That gives me positive, okay? At 0, which is in between -1 and 1/2, right? So it's on the right side of -1, but the left side of 1/2. When I plug in 0, that's easy. All of this, well, this will be 1, 1, 1. I could just kind of go cheat a little bit and go up to my original. If I plug in 0 everywhere, I get out a -1, right? So that's easy. When I plug in 0, okay, I can still look at the signs, which I do, but I already know it's negative because it's just that constant term, okay? So now I need a value in between 1/2 and 1. So again, 3/4 is right in the middle. So let's check that. 3/4 is less than -1, so this will end up being negative. And it's squared, so it actually will be positive, so it doesn't really matter. Positive and positive, so that's a positive. Here, well, let's see. 2/4 is really 3/2 minus 1, so 1.5 minus 1, that'll be positive. Okay, so overall, this will be positive. So far I have one interval where I have negative values, right? And that's in between -1 and 1/2 so far. Because remember, -2 is on one side, 0 is in between -1 and 1/2, and then on the other side of 1/2, I got positives. So far between -1 and 1/2, I will have negative values out. So let's check on the far side of 1 now. That's the last thing I have to do. So here will be positive, positive, positive. All of those signs are positive. So I get a positive out. Okay. So the only times that I have that negative then is between the -1 and 1/2. This has equality on it. So my interval that satisfies this polynomial being less than or equal to this is the closed interval from -1 to 1/2, right? So whenever x is one of these values or between those values, it satisfies this condition, okay? So now we have enough information to graph our zeroed polynomial, this polynomial, okay? So we can graph this result for us, okay? Graphing this would be a lot harder because we'd have to graph two things and, you know, what have you, but we can graph this polynomial and look at the intervals that satisfy this, right, which is this interval. So just so we have a graphical representation for this being less than or equal to 0, I know what my zeros are, okay? I know I'm going to cross the axes at the odd zeros, right? The odd multiplicities of 1, and I'm going to bounce off at the even, right? So it crosses at x is -1, at x is 1/2, and it bounces off the x-axis at x equals 1. I know what my y-intercept is, okay? My y-intercept is 0, 1. This acts like a fourth degree polynomial. The lead coefficient is positive, so it looks like a u. So when x goes to infinity, I have large values out. When I plug in very large negative values, I still get out positive values, right? It's u-shaped because it's an even powered, even degree polynomial. So that's really all I need in order to graph, right? I plug these values and I follow that behavior. So the first one are the zeros, right? I have a 0 here, a 0 at 1/2, and a 0 here. So these are the zeros it crosses. This is the 0 that bounces. I have my y-intercept, and I know my end behavior is up. So up, it crosses, okay? It has to cross here. Here, it bounces, and it ends up, right? So it's up, up, crosses, crosses, it hits this value. Here, it has to bounce off, okay? So that's the exact graph. And again, once you get into calculus, you'll be able to find values like this extremely easy. Values like this where it changes shape extremely easy. So you get a better idea of how to graph things. Here, obviously, if we drew it by hand, we'd probably just do just a quick loop here, right? But, you know, we can draw the exact graph. So this is what the exact graph looks like, okay? Again, when I ask you to draw these things, I don't expect you to give me exact graphs, just to be able to provide the information that we're able to find analytically by analyzing the function, and just make sure that the graph looks something like that, right? Now let's say that we didn't look at the single polynomial, right? This thing that we solved for, that we used, you know, that we used to analyze the actual inequality. But let's go ahead and graph these two, okay? We're not going to go through the process one at a time. We'll just plot the two ones. So these are the points of intersection, right? Which is where we look at when one function is larger than the other, okay? So this is our first function, and that's our second function. And here you can see when we have one function being less than the other one. So remember, it's from -1 up to 1/2. So from this point to this point is the only time you see the red function being less than the blue function. There's no other time when you do that. So this is one of the only times I included color. I actually can include color whenever I want to. But I'm only including color so that we can differentiate between the two functions, especially since they're so closely matched like here, okay? So again, the red function for our example is this first fourth degree polynomial, and the larger one is this, I'm sorry, the blue one is this one, and this is the red one. So when is the red one less than the blue one? Okay, so that's our first one. This is the other one. Okay, so let's look at another example. Okay, but again, notice again that the points work, right? So let's look at another example. So we want to solve in a rational function problem, right? So we have one rational function being more than or equal to another rational function or expression, however we want to deal with that. So it's the same thing. We want to zero it out. It will be way easier to take this and move it over than to subtract both of these to the other side. So we move one over. Next, we need to, we don't want to clear denominators. I know normally I say there's an equal sign and fractions, clear the fractions out. It's not going to work that way because then you get weird answers, right? So we talked about why that is in 1.8 a little bit. We had touched on it. And a lot of it has to do with the square property of x, right? And having, basically just having two values of x working in two different directions. We have to take the negative into consideration and the positive into consideration. So it's hard to see what's actually happening. So we don't clear the fractions out, okay? However, we do make a common denominator. So my common denominator is x plus 1, x minus 3, x plus 2. So to 1, I need to multiply 1 times the two denominators that's not there, right? To 2, I have to multiply the two denominators that's not there, and to 3, I multiply the two denominators that's not there. I know what the common denominator is already. I know what I have to multiply. I don't write a lot of extra stuff if I don't have to, so we can snap straight to here, right? This is 1 times the two denominators I'm missing, plus 2 times the two denominators that I'm missing, x plus 1, x plus 2, minus 3 times the two denominators it's missing, x plus 1, x minus 3, all over the common denominator, okay? So the next step from here is exactly what you think it is. Simplify, okay? This is nice because there's no 2's in front of everything, so it works very well. X squared, I can add these together, so that's minus an x. Multiply those is negative 6, okay? Same thing here, the 2 stays, multiply this, x squared, 1 plus 2 is 3, and then 1 times 2 is 2. Same thing here, negative 2x, negative 3, right? The next thing I want to do is distribute my outside term, this 2 and this negative 3. So that stays the same. This, everything multiplies times 2. This, everything multiplies by negative 3. Okay, my denominator stays the same. It's still larger than or equal to 0. And then from here, obviously, the best thing to do is combine like terms, right? So x squared, 2x, minus 3x disappears, right? Negative x plus 6x plus 6x. So this would be 12 minus the 1 is 11. Negative 6 plus 4 plus 9, so that's 13 minus 6. So we have 11x plus 7 over our common denominator. Okay, so now we're going to analyze this function by analyzing this result. Okay, much easier to analyze this than to do this and try to compare them, right? So for this one, the zeros are easy. It's negative 7 over 11. Okay, the vertical asymptotes are 3, negative 1, negative 2. Okay, negative 2, negative 1, negative 3 if I write them in order. If I plug in 0, right, I get 7 on top. I get negative 6 on bottom. Oh, I didn't write it, but that's okay. I get negative 7, 6. The real important is the sign check, right? I really want to know when is this larger than 0. So now that I have the vertical asymptotes, I need to check between them and the 0, right? So between the 0 and the vertical asymptotes to find the points when this thing is positive, okay? So to the left and the right of negative 2, so probably negative 3 and negative 1.5, right? To the left of negative 1, so I already have one on the left, so the one on the right, and between negative 7/11, right? So in between negative 1 and negative 7/11. So let's look at this. This is a little bit more than 1/2, right? Because 1/2 would be something like, well, 6.5, right? 5.5 over 11, right? So 7 over 11 means it's a little bit more negative than 1/2. So I need to find something in between negative 1 and negative 7 over 11. So probably something like negative 3/4. Then I need something between negative 7 and 11 and 3. So probably something like 0. And then something to the edge of 3, right? So something like 4. So again, we're just going to look at the signs. So x equals negative 11. Sorry, negative 3, because that's on the edge, to the left, I'm sorry, of negative 2. So again, I'm really just going to plug stuff into here. Okay, so hopefully you have this written down. So negative 3 gives me negative 33 on top plus 7. This is going to be negative. It'll make this negative. It will make this negative, and it'll make this negative. So I have negative, 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 negative. Right? That'll give me a positive. Right? So I can talk about just the signs, right? Because I can talk about what happens as I approach negative 2 from the left, knowing the sign check here. More importantly, it tells me that I'm positive, right? I'm larger than 0, which is what I want, right? I want positives. So that's telling me this is a point in time when I'm positive. So I'll go negative 3/2 because that's in between negative 2 and negative 1. So I get the following out. So again, hopefully you can check this yourself. So negative 1.5 compared to the values that we have for the numerator, right, and the denominators. So this will be a positive, negative on top gives me a negative, okay. Negative 3/4 is in between negative 1 and negative 7 over 11. So I get plus plus, these two are plus, so that's another interval of plus. Negative 1/2, because that's on the other side of negative 7 over 11. And I get these signs, which will give me a negative, right? So far I've been plus, minus, plus, minus. So now I need something in between negative 7 over 11 and x equals 3. X equals 0 is the easiest one to use for that. So I get another negative. And then I need something on the other side of x equals 3, so I use x equals 4. And I get all pluses, so I have my plus. So again, remember, I'm interested in when I'm larger. So the points that I am positive, right, larger than 0, are from negative infinity up to the point in between these two, which was x equals -2. From the point between this and this, which was from -1 to -7/11, and the point from here forward, which was 3 to infinity. So writing that as our solution, right? This is satisfied whenever x is from -infinity to -2, inclusive because of the equality, -1 to -7/11, or from 3 to infinity, right? So again, at this point now, we have enough information to graph our zeroed out inequality, not necessarily this one, because we'd have to do a whole nother set of 2 analyses. But I do have my zeros, right, which is at -7/11. I have my vertical asymptotes at -2, -1, 3. The end behavior, if we come all the way back to what we have here, is that the denominator dominates, right? Dominates the function. So as I go to positive infinity, I'll go to 0. As I go to negative infinity, I will also go to 0, because the bottom number will get larger than the numerator will. Okay, so the limit of this, as I go to either of these infinities, will be 0. And if we look at the limits around my vertical asymptotes, I actually already have all that information, right? I've already looked at what happens around my function between the asymptotes and the zeros. So I just use this same information from our sign check that I had in order to talk about what my limit's going to be, right? So it'll be, again, for 2, it'll be positive infinity from the left. It'll be negative infinity from the right. For -1, it will be negative infinity from the left and positive infinity from the right. For -7/2, it'll be positive infinity from the left, negative infinity from the right. From what's the next value that we had here? We have it here, right? So for 3, it's from negative from the left and positive infinity from the right, right? So here. So positive, negative, negative, positive, negative, positive, right? And again, these are the same. They just coincide with the sign checks that I have, right? Plus, minus, plus, minus, minus, plus. Okay. Plus, minus, minus, plus, minus, plus. Right? So they agree. If we look at our graph, put my first asymptote, my next asymptote at x is -1, my third asymptote, I have only one 0, which is at -7/11, which is over here somewhere. Okay. So this is what I look like here. This is what happens here, right? So that's the 0. And my asymptotes, my horizontal asymptotes are 0. As I approach this from the left, it's positive. From the right is negative, negative. Here was positive infinity, negative infinity, positive infinity, and 0. Okay. And that's the way that works. Thanks, guys.